Hi, I'm Jennifer.
My name is Grant.
I'm Ben.
And I'm Corey.
We did our term project on floating point arithmetic relative error. We referenced the book Rounding Errors in Algebraic Processes by James Wilkinson that we found on Google Scholar. We also used the algorithms that we learned and developed in Math 374 to calculate relative error.
Okay, so the first method that we use is a iterative method that uses a nested for loop to calculate its values. So it basically goes cell by cell in the matrix and adds the value to the running sum, which is right here. And that is pretty much the key difference, is that it does this addition item by item as opposed to lump sums. And the first method, as noted here, returns a relative error and then a runtime, and that's compared to the true answer that's calculated right here via a library function.
The second method we used is the lump sum method that he talked about earlier. It does the same thing, it times it, and it goes row by row, adding up the entire row, one at a time, and then at the end it adds up all the row sums. This, once again, the relative error is calculated right here, and it's using a calculated or pre-calculated true answer to determine how close the error actually was.
And I'll demonstrate the program running. I'm clicking the play button and typing in 100,000 and pressing enter.
This value for n is just n is the amount of rows and columns each cell.
So in total, that's about 10 million cells in the matrix, which is represented via 2D array. And it takes a long time. It's a lot of math.
This is just showing the sheer size the computer can handle. So 10 million elements in this array.
And it's done.
So as you can see, method 1 gives a pretty nice error, 9.9 times 10 to the negative 1, and a runtime of, 30 seconds. Total execution time of 66 seconds. But it also shows that the second method used has quite a lower relative error and a much faster runtime. And that's our program.